Good morning, everyone, and thank you for attending today's presentations by Till and I. In my presentation, I'm going to show you my ongoing work on my diploma thesis, which is conducted at the University of Patras in Greece under the supervision of Professor Fatsois. Before we dive into the specifics, I would like to do the outline first about my presentation, which concerns the use of non-stationary excitation contrasted to stationary excitation for optimizing damage detectability. We will start with the introduction of the topic and the rationale behind our idea, and then I will outline the methodology of our approach, detailing all steps and processes. This groundwork is then to be applied to a simulated BIM model, which was designed by me in Abacus. And finally, we will discuss about the work that remains to be done in order to complete the research. So, to introduce you to the problem, random signals are used for diagnosing damage, structural damage. The fundamental principle upon which its methods are based is that a damage in a structure or even an incipient damage may cause some discrepancies in its vibration response, which may be detected and then associated with a specific type of damage. This damage can also be localized and quantified. So the main point here is that a change in the response of a structure is an indicator of its health condition. But this relation is not straightforward, since the dynamics of a structure may also be affected by some environmental and operating conditions. The SHM problem then becomes more sophisticated. In this context, when the excitation is in structural health monitoring cases is fully user specified, stationary signals are used as excitation, with the random white noise being the most common one. This study aims to explore whether the use of non-stationary excitation may lead to improved damage detection ability. In real infrastructure problems, where ambient excitation is in most of the times non-stationary, as we can see in these two pictures, there is a traffic-induced bridge and civil infrastructure under some seismic load. In both cases, the excitation is non-stationary. With all this being said, the question is still important, but rather of theoretical importance than practical, and concerns whether the non-stationary nature of these excitations facilitates the damage detection ability. But this may change in a laboratory setting, for example, where the excitation is fully user specified. Practicality is then restored. The underlying idea behind is that non-stationary excitation is characterized by richer structure and more complicated properties. These properties involve the autocovariance function and the power spectral density function, which show time dependency. The mean value may also be time dependent. These rich due to time dependency characteristics compared to the stationary counterparts where there's no time dependency are carried over to the response. and may be more prominently affected by damage, thus leading to improved diagnosis. To illustrate this and make you understand better, here on the left, we can see the power spectral density of a non-stationary signal. We can see that we can treat this spectrum, which is a function of two variables, time and frequency, as frozen type power spectral densities at every time instant. So it is easily understandable that it's easier to detect a damage when we have this instead of just one power spectral density function. In our study, we employ a non-parametric statistical time series damage detection method with the characteristic quantity being the power spectral density function of the structural response. Our excitations we are testing are of two types. First, conventional stationary white noise, and then a non-stationary produced via TAR model spectrum. We have also employed two structures and 1 degree of freedom mass damper system in MATLAB and a composite beam designed in Abacus. Both structures are used under healthy and unhealthy structural states. Damage detectability is then expressed as a distance in the response PSD between the healthy and damaged structural states. The idea here is very simple. The higher the distance between the response PSDs, the higher the discrepancy between them, and this leads to improved damage detectability. In our work, we are firstly computing the theoretical output spectrum using mathematical formulas. We do this for both the stationary and the non-stationary case. The linear mass damper system is excited using spectrum of non-stationary TAR2 excitation and spectrum of stationary white noise excitation. And then we derive the output spectrum in both cases. We also do this for a damaged structure. For the stationary case, there is a very common, there's a very well-known formula which relates the input to the output spectrum, but we can't use this in the non-stationary case, and that's the problem here. But after doing a lot of search, we finally found this formula, which is the same, but for the generalized non-stationary case, and it suggests that the output spectrum, which is function of two variables in the non-stationary case, is the convolution of the input spectrum and the spectrum of the impulse response of the structure. After that, after having calculated the output power spectral densities in both the stationary and the non-stationary case, we also calculate the spectral distance between the healthy and damaged states. In the stationary case, the distance is degraded to a function of only the frequency. This type of distance can be, for example, the Euclidean distance between the peaks of the power spectral density of the healthy and the damaged states. And we don't have any results yet. I have inserted plot from a very similar research work, which shows that indeed the distance is higher in the non-stationary excitation case. The distance between the damaged and the healthy output power spectral densities is higher in the non-stationary case, and this suggests that non-stationary use of excitation may potentially lead to better damage diagnosis. Now I'm going to quickly talk about our excitations. For the non-stationary case, we selected an input spectrum of TAR2 model, which is synthesized by a natural frequency varying with time. This is the natural frequency of our excitation. And here we can also see the power spectral density of the input. As I have already said before, the employed structure is a mass spring damper system of 1 degree of freedom in MATLAB. Here we can see the properties of the system, and the non-stationary instantaneous spectrum of the impulse response function of the system is also plotted, which will help us calculate, as you can see from this formula here. We have the input spectrum. We also have now the instantaneous spectrum of the impulse response of the structure, so we can calculate the output spectrum of the system. This slide summarizes what has already been said. Here we can see what we used for input in the stationary case and for input in the non-stationary case. And here is the resulting output power spectral density function. And here is the non-stationary, which, as already stated before, can be treated as frozen type power spectral density functions at every time instant. We can also notice that these output spectrals are influenced by the dynamic of the structures, since we see a peak at the natural frequency of the system, which is approximately at 1.6 Hertz. You can also see the peak in the non-stationary case. And now I will give you a quick overview of the composite beam model, which was designed in Abacus. And the dimensions were derived from measurements of laboratory beams. We see the material used and the configuration of the plies, which is symmetrical. I don't want to focus so much on this, and there is one excitation point. There are also 3 measurement points from where we are going to measure the acceleration response of the beam. There is also one damaged area. The damage scenarios are 3, and are all of the lamination type damage of 3 different magnitudes. This damage was represented by overlapping duplicate nodes, so that the plies can open during an analysis of the model. We also have some preliminary figures of the beam. Here, in the first 3 plots, we can see in blue color the the frequency response of a real laboratory beam, and in black color of our simulated model, and they seem very well aligned. But this was not the concept here to have a digital twin of the real structure, but we have some exceptional results without even having the correct properties of the beam. And also, the three delamination type damage scenarios are confirmed. As we can see, we see some deviations between the healthy and the damaged structural states. This means that our damaged scenarios are okay to use. And as we are going towards the end of the presentation, I would also like to quote what needs to be done in order for this work to be complete. We need to consider some damage scenarios also regarding the 1 degree of mass number system in MATLAB. We also need to calculate the output power spectral densities in all structural states and compare the results. A genetic algorithm may also be used for optimizing the non-stationary excitation design, with the optimized parameter being the natural frequency of the non-stationary excitation. And regarding the finite element model, we will run some Monte Carlo simulations on the composite beam. And after that, we will assess the benefit of using non-stationary signals instead of the conventional stationary excitation. This was my presentation. Thank you very much for your attention. Feel free to ask me your questions.
Thanks all for coming. Welcome to my master thesis project presentation. This is my midterm presentation, so it will not be as result focused as Iasonos, since I'm still in the works, but I will do my best to just kind of outline the whole idea. And yeah, let's go. So my name is Pitzke. I'm a master student in mechanical engineering and business administration, and I'm specialized in energy technology. So wind turbines, gas turbines, engines, and this sort of things. My home uni is RWTH Aachen in Germany. And yeah, I'm visiting here for 1 year, and I'm spending 6 months in your department. My supervisor for my project in Aachen is Andreas Klein from the Institute of Automation Control, and he works on load-reduced control for wind turbines. And here at RWTH, I'm supervised by Imad Abdallah, who is a postdoctoral researcher on the structural health of wind turbines, and also by Julien Pipadai, who's an expert on experimental fluid dynamics from OST. If you have any questions, just let me know. I can answer right away. The project duration is September until March, so I have around 3 more months to finish. Brief agenda. So we'll start first with the context and the motivation, and then I will go into these 3 pillars that kind of outline the whole project: data kinematics, inertial measurement unit, and sensor fusion and state estimation. Talk a bit about my data sources and experimental setup, and last but not least, go into the challenges, and sure there will be an open forum to discuss the topic. Okay, so as I said, my title is Inertia-Based Estimation of Wind Turbine Blade Motion, and the background of this project is AeroSense. AeroSense was a project between ETH, Zurich, OST, and various other institutions to develop a wireless measurement system for wind turbine blades. You can see it here in the picture. So few of you were quite deeply involved in this. Here it's mounted on a turbine blade. It's a prototype. We have pressure sensors, so an area of around 40 to 50 pressure sensors. We have a power supply, solar panel, and here we have a microcontroller that can process, collect the data, and also transmit. In addition to an inertial sensor, which I will use during my thesis. The key problem is that while this sensor system works, for a detailed aerodynamic analysis of the pressure data, you need detailed knowledge about the blade orientation and its motion through space. And this cannot be accurately captured from the machine itself. Once, because the interfaces are not, say, accurate enough, and then we have all sorts of deflections and other effects that vary locally and in time, depending on where you are on the blade and what the conditions are. So the idea is to develop a sensor fusion algorithm to use the inertial data from the node to determine the orientation and motional state in real time, then goes to benchmark and test it on real data and assess its uncertainties and sensitivity, and therefore kind of outline the usefulness of such an approach for the purpose. Limitations are for now limited to a single point, so I'm not capturing the state of the whole blade, but more a section on the blade, so blade element or one point, and the estimation is relative to the tower. It's not absolute. So for example, if you use a technology like GPS, you can get an absolute estimate. This is purely relative to the rotational center on the rotor. Yeah, some side missions. This real-time deflection estimation can also be used for control. For example, to avoid tower collisions or to reduce the structural load while maintaining power output. This is something my home supervisor is working on. So outline, we start with the inertial sensor and we know where we want to go. We want to achieve an estimate of the blade position. And there are basically two approaches that we can follow. The model-specific approach, which heavily involves structural dynamics. We can simulate the whole blade, its aerodynamic conditions, its motion, especially the deflections. For this, we need rather detailed knowledge of the blade, material, and real-world behavior. This greatly varies from the, let's say, manufacturing specifications, but it has the benefit that we get the whole deflection. We can estimate loads and stresses. The second approach is model agnostic, where we just pretend that our sensor basically free floats through space, that it's not even attached to anything, and it rotates about some point, and that's all we know. So we completely, say, ignore the blade, and then later use the fact that this sensor is attached to one blade segment to work backwards to extract the blade state. And what's special about this kinematic approach is we have pure motion, so no forces, no masses, no impulse, no energy, which makes it easily applicable to any blade without structural information. And we can use known kinematic restraints, for example, from the degrees of freedom, to couple the different dimensions. And that's what we work with. And I chose this approach. Yeah, something you sometimes see literature that you use kinematics to kind of filter the inertial sensor data, and then later use improved measurements for example, some model simulations. Might do that if I have the time, but for now it's not scheduled. Okay, so next we will go into the blade kinematics. Any questions so far?
Maybe best for the recording, you keep them for the end.
Okay, keep them for the end. So as I wrote here, blade kinematics, the question of varying complexity. So as with any other model, there are different complexities that we can choose, and the more complex we make it, the harder it becomes. We can have this simple turbine that has just 2D, it has 1 degree of freedom, it can rotate, that's it. Then we can have the 3-dimensional turbine with controls. It can pitch, that means it like kind of tilts its airfoil to get a optimal position in the wind flow. It can yaw to turn towards the direction of the strongest wind, and then it can also rotate around. Here you see it's a tilted axis, and then last but not least, you can have something crazy like a floating offshore platform where the base can move, the tower can deflect, and then the blades have torsion. They can deflect flap-wise and edge-wise. And for now, I will stick to the simple model, and I think it's sufficient to understand the whole concept, and it doesn't really change with added complexity, it just gets more, it just takes longer, and I will make a lot more mistakes. So let's take this model. This is our turbine. We have gravity. If I was a real engineer, it would just be a line and a dot and another line. Yeah, it's a meter. And we put the sensor on top of the blade. Let's put in some coordinates. So we have base coordinates. It's attached to ground, to an inertial system, roughly the Earth. Then we have the tower, which is rigid, and the sensor rotates around the tower. We can describe this in polar coordinates. So we have our ER and our AFE, which disappeared. And the whole state can be represented with 2 variables. One is the phi, the angle, and the other one is omega, our rotational speed. And with the state transition matrix, I think it's here, we can also get all states in the past and in the future. If we look now at what the sensor experienced during this continuous rotation, we have an acceleration in the sensor frame that is composed of a centripetal component that always points to the rotation center. That's the red one. And then we have a gravitational component that splits between E1 and E2 and depends on the angle phi. And since this inertial sensor can also measure angular speed, we have the rotation on E3, which is perpendicular to the plane shown here. And if we think now, how can we kind of get this state from the measurement? Quite simple. Okay, we measure the omega, the angular speed. Then we use the known radius to remove the centripetal component from the acceleration. And then we can use, for example, a tangents to arc tangents to get the phi. Okay, let's check how this relates to our measurements. Now we'll go to the measurement fundamentals now. So the sensor is the sensing technology is kind of based around this MEMS, because MEMS is very cheap. It takes very little power, and cheap is something you always want for energy technology. And also, since it's on the blade, you cannot really run cables for any power-hungry equipment. So the MEMS is what we will have to work with. MEMS stands for Micro Electromechanical Measurement System. And it's quite interesting to see it, like those tiny sensors, they actually have moving parts in them. So you can print pretty much anything. You can print gears, you can print valves. And one measurement system is the IMU, which is commonly used in drones and phones. And it consists of usually an accelerometer. And as I said, it's a moving part, so you have a suspended mass. And due to inertia, if you move or if you accelerate the sensor, this mass will kind of lag behind. You have springs here. The springs are then extended. And between these whiskers here, you can measure a change in capacity. The gyroscope works in a similar way. The only thing that changes is that this whole mass spring system is oscillating on a fixed axis. And if you rotate the sensor now, you will experience a Coriolis effect that will move the mass perpendicular to the projected rotational axis, so this forward-backward movement, and the enforced rotation. And then last but not least, it's not inertia. You have a magnetometer that uses the Hall effect to establish the direction of the strongest magnetic field. Why is this so important? The big problem with MEM sensors is that since they're mechanical systems, they are really susceptible to vibration, temperature. You have crosstalk if you have extreme accelerations in one direction, as we have in a rotating wind turbine. It will also influence the readings on all the other axes and also the other sensors, for example, the gyroscope. So we really have to expect measurement noise. And the key takeaway is that we cannot operate directly with sensor data. You have a simple sensor model, so we have a true value with some random noise and a bias, for example, but an accurate sensor model would involve a lot more terms dependent on all kinds of environmental variables. How can we mitigate this? We have to calibrate. That's something often neglected in literature, because a lot of calibration can be done on the sensor itself, and it changes the output. But after that, it's no longer really possible to see what this calibration was. That's the difference between hooking up analog sensors directly. And then another method is sensor fusion, is that we combine different noisy measurements to decrease uncertainty in one. So if we look back to our example for the 2D turbine, I plotted the true angle of rotation in blue, and I added some random noise to the angular speed and to the accelerations, and try to use these perturbed measurements to directly estimate the angle. And you can see it here in orange. Actually, it aligns quite well in the mean, but it shows a behavior that doesn't really resemble our turbine. So, for example, the turbine cannot really move back and forth. And then in green, I employed a simple complementary filter where I used once the acceleration and then included propagation using the angular speed from the for the state development, let's say. And for even improved accuracy, it makes sense to use dynamic filtering. For example, the Kalman filter, which is a recursive filter that propagates the state based on a state transition model and then uses measurements to correct it. So this topic of inertia-based estimation is not new. I put some previous work. So one thing that is special about this topic, so the feasibility has been properly assessed, I would say, but all the solutions we have right now are more isolated estimations of individual variables without really taking into account the connections. So for example, with Bergman and Lang, we have one extended Kalman filter for rotation speed. We have a complementary filter for pitch. We have no yaw, so it's only for steady state without yaw operation. And then we have separate filters for edgewise deflection and flatwise deflection. And the severe limitation, that's steady state and only really works for small deflections. For example, due to the use of small angle approximations. And the other extreme is Rundfilter and Melbert, which is an approach that is based on spline fit linear spline fit these squares. And what they did, they put sensors on a blade and used the steady state deflection as a type of mode analysis at standstill, and then basically argued that all the deflections and all the blade movement will somehow correlate to this it's not the first mode, but this gravity mode, let's say. And this is worked well in the example, but it's really limited because it heavily depends on your experimental measurement, and also this assumption that your blade behavior and deflection during standstill closely resembles the one during extreme operating conditions kind of deteriorates. So my goal is to kind of assess the existing methods and develop one or two improved Kalman filters, probably extended Kalman filters, and then also include this torsion here, which has not been addressed by literature, and estimate yaw from magnetometer readings, because right now yawing is not probably accounted for, and on modern turbines you have operating conditions where you have this continuous usage of yaw to align the turbine, and it's just a state that these approaches cannot handle. The first two I already implemented, and I will test them in the near future. Any questions for later? Now we'll show some of my work so far. So I started with a really detailed representation of the kinematics. You can see it on the top left. It's like a coordinate system overview. If you want to see it, you can approach me later. It's just, I think it's 15 or 16 different coordinate systems that I will base all my work on. And it's in close alignment with IEC norms and published standards by NREL. Second thing is the sensor model. We'll start with simple, maybe expand in the future. To the practical part. The validation is difficult because access to such a big turbine is limited. So I decided to test my algorithm on a scale model. You might know it from the Bauhalle. For this, I built a miniaturized version of the AeroSense system. It's basically a small microcontroller that's the size of a fingernail, hooked up to an IMU. It has a battery, and it connects to Wi-Fi and then sends 9 degrees of freedom IMU data at 100 Hertz directly to database. And you can see it up there. It works quite well, and I will use this to test calibration, and I will use it to test my filter behavior in different operating conditions. Later, my goal is to validate on a large simulation. For this, I will use OpenFast. From OpenFast, I want to basically extract the trajectory of a point on the blade and then use MATLAB to simulate IMU readings for this trajectory. So trajectory will be my ground truth, and the readings my simulated measurements. Some challenges I'm facing. Academics are right now really working harder to improve my mathematical understanding of model-based estimation methods. It's not so important for the development, because you can still get the filter to work, but to prove why it works and when it works, what the limitations are, you need a really solid understanding. And then with the method, that's difficult, is the complex interaction between the different coordinate frames. For example, if you have a blade that is deflected like this, and then you apply torsion, it has an influence on all three measurements that you take from the sensor. And another challenge is including multiple IMUs. So 2 weeks ago, Matteo had a really interesting talk about this topic of timing the different readings, it would be quite interesting, especially if you have a turbine that is has a flexible tower, to have a IMU in the tower, and then also if you have an offshore floating turbine, you need a IMU in the base. All right. So thanks for your attention. I will open the floor for discussion.